Welcome to lesson 3.10. Today we're going to talk about stoichiometry. Stoichiometry is basically using molar masses and balanced equations to determine maybe how much of another reactant you might need, how much of a certain product you're going to get, things like that. So in order to do stoichiometry, you need a balanced equation. You also need to know the masses of the reactants or products, and you need to know how to set those up in appropriate ratios. This particular diagram is a little more complex than what I usually use. I use a diagram where basically I start out with grams of A, and then I need to get to moles of A, and then that helps me get to moles of B, and then I get to grams of B. There's other things that can go on as this particular diagram indicates, but this is kind of the basic setup for stoichiometry. At this step and at this step, you're looking to get you from this part to this part, use the molar mass of A. To get from this part to this part, use the molar mass of B. In this particular conversion, you need to have a balanced equation. Okay, so that's what I use to go from reactants to products and so on. And so sometimes the hardest part is figuring out what's your A and what's your B. So I have some slides here that walk through one problem, the step-by-step problem-solving method that we've kind of looked at before, and then there's a problem that we'll do from scratch. So solid lithium hydroxide is used in space vehicles to remove exhaled carbon dioxide from the living environment. It forms solid lithium carbonate in liquid water. What mass of gaseous carbon dioxide can be absorbed if I have a kilogram of lithium hydroxide? Obviously, this is a very important dilemma for space scientists or astronauts, because if you don't have enough lithium hydroxide, then you're going to fill your atmosphere with carbon dioxide. So where are we going? We're going to find the mass of carbon dioxide absorbed by 1 kilogram of lithium hydroxide. What do we know? There is a chemical reaction. That particular chemical reaction is not balanced yet, but there's a chemical reaction. We know we have 1 kilogram of lithium hydroxide. What information do we need? So we need a balanced equation. And there is the balanced equation. We need to find the moles of lithium hydroxide. Now notice in this walked through example, they're going to go step by step. I prefer to go step by step, but I like to kind of put it all in the same problem. So to find, we're given mass of lithium hydroxide. To find moles, we need to calculate the molar mass. So a lithium plus an oxygen plus a hydrogen. And we're going to take that one. Now, molar masses are given in grams per mole, so we need to convert kilograms to grams. And so we're going to use the conversion. Some people just do this in their heads. They just automatically say there's 1,000 grams of lithium hydroxide. Here shows the conversion. And then we're going to do that next step. So this is going from grams of A to moles of A. And so here's that molar mass that we just calculated. And then the mole ratio, that's what I mentioned you got from a balanced equation. So for every 2 moles of lithium hydroxide, we get rid of 1 mole of carbon dioxide. This was what we just calculated in the previous step. There's our mole ratio, and so that means that we pull out 20.9 moles of carbon dioxide. And the mass of that, we're going to use the molar mass of carbon dioxide, and we come up with 9.20 times 10 to the 2, or 920 grams of carbon dioxide being absorbed by 1 kilogram of lithium hydroxide. All right, so here's the example that we're going to work on our own. Excuse me. One of the things I like to do is I like to kind of look ahead in the problem and figure out which molar masses I'm going to need, because I don't want to have to stop and calculate those later. So there's the reaction. it wants to know what mass of iron 3 oxide and aluminum must be used to produce iron. And then it wants to know what the maximum amount of aluminum oxide could be produced. So it looks like we're going to have to use all of these. So let's go ahead. We notice that there are some coefficients in this equation, so it already is balanced. But let's go ahead and calculate the molar masses of each of these. So iron and aluminum are pretty easy. Iron from the periodic table is 55.8. So the molar mass of that is 55.8 grams per mole. Notice I did not take into account the 2. The 2 is not necessary. I just want to know how much an iron, what the mass of an iron is. And then the aluminum is 27 grams per mole. Okay. Let's go ahead and calculate the other two. So if aluminum is 27 grams per mole, so 27 times 2 is 54. And then 16 times 3 is 48. So I end up with 102 grams per mole of aluminum oxide. And then the iron, on this one, I'm going to say is 56 times 2, so that's 112. And then 16 times 3, so there's that 48 again. And that is 160 grams per mole. Notice I didn't take into consideration any of the coefficients. You might want to jot these down as we're going to go to the next slide, and they're going to disappear. So the iron 3 oxide has a molar mass of 160 grams per mole. Aluminum is 27. Iron is 55.8. And then aluminum oxide is 102 grams per mole. And I'm going to write down the balanced equation. Fe2O3 plus 2 aluminums gives me 2 irons plus aluminum oxide. Alright, now that I have that written down, I'm going to go on to the next slide. It wants to know the mass of iron 3 oxide and aluminum that we need in order to produce 15 grams of iron. So this is our A. That's our A in both cases. We're going to say this is our first B, and that's our second B. And so we have to go one at a time. So let's start off with 15 grams of iron. So 15 grams of iron, and we need to go to moles. We use the molar mass to go to moles, so 55.8 grams of iron and 1 mole of iron. And we're going to go to iron 3 oxide this time. So we're going to look at the equation, and we need moles of iron here on the bottom. What number is in front of iron in the equation? It's a 2. And what number is in front of iron 3 oxide? It's a 1. So this is where those coefficients come in. It wants to know what mass, so we need to go one more step. 1 mole of iron 3 oxide has a mass of 160 grams. Now the way I'm going to put this into my calculator, I'm going to take everything on top times each other, and then I'm going to take everything, divide it by everything on the bottom times each other. So on top I have 15 basically times 160. And then I need to divide that, and then I'm going to use parentheses, divided by 55.8 times 2. And my calculator just died on me. Let's get another calculator. 15 times 160, and divide that by parentheses 55.8 times 2, close my parentheses, and I come up with 21.5 grams of Fe2O3. Okay, start off the same way with the next part of the problem. So 15 grams iron, 1 mole of iron has a mass of 55.8 grams of iron. And again, I'm dealing with iron, so 2 moles. What is it I want to go to this time? I want to go to aluminum. The number in front of aluminum is a 2 as well. And then I finish off with aluminum. So 1 mole of aluminum has a mass of 27 grams. Okay, so in my calculator, 15 times 2 times 27 divided by parentheses 55.8 times 2, close my parentheses, and I get basically 7.26 grams of aluminum. Let's go ahead and click on the button to see if we're correct. Yep, mass of iron 3 oxide is 21.5 and aluminum is 7.26. Now it also wants to know what the maximum mass of aluminum oxide that could be produced. So again, we're going to start with the information we're given. So 15 grams of iron. Still, same few steps. So we need to get to moles of iron. And then 2 moles of iron, because there's a 2 in the equation, because this is the step that we get from the chemical equation, gives me 1 mole of aluminum oxide, and then 1 mole of aluminum oxide has a mass of 102 grams. So 15 times 102 divided by parentheses 55.8 times 2, close my parentheses, and I get 13.7 grams of aluminum oxide. Let's check our math. 13.7 grams of aluminum oxide. And that concludes this short lecture over stoichiometry. Stoichiometry is one of those things you need to practice and double check your answers. The diagram that was shown in this particular PowerPoint was involved limiting reactants. I would use the one that I gave you that goes from grams of A to moles of A, then to moles of B to grams of B. And we'll look at that in more detail in the next lesson when we start talking about limiting reactants and excess reagents.